Cool. How's everybody doing? Ready for a break? Yeah. This is a point in the semester. It's a slog at this point. You guys have done really well this semester. Thanks for bearing with me on a Wednesday lecture. So probably people aren't super excited to be here on, but this will be good. This will get us caught up. What often happens is we run into these factorial designs, which is kind of an amalgamation of everything that we've talked about up to this point, and you're kind of putting all these pieces together, but it can get kind of complicated to wrap your head around and sort of lock into this idea of interactions, how we go through and approach things, different considerations, and teasing things apart, and it always feels bad to be kind of rushed through things at the end of the semester. I think we're in a good spot. We'll get through a good chunk of stuff today, finish up on Wednesday, and that should give you a good sense for these designs, how to approach them, with any of this experimental stuff. Depending on what type of design you're using, you can get pretty deep into the weeds with stuff. I was working with Sean one time on a thing that they were doing in his lab, and there was weirdness, and it kept referring to some text from the 60s, and then when you go to the source page, they're basically yeah, I don't know, this is weird, right? And so depending on sort of the design and sort of some of the issues that you have to think about, it can get quite complex. We're going to go through and just alert you to kind of the basic things to be aware of as you're approaching these designs, some of the things to think about. But at the end of the day, and I think this is what I really like about the approach in that Howell text, is that Howell will make the argument, when push comes to shove, it's perfectly fine to just fall back on t-tests. Right, you lose, some potential power that you would get with sort of traditional sort of approaches, but at the end of the day, you're probably not gonna. You probably won't get slapped if you just say, okay, I'm going to go through and I'm just going to look at this stuff, figuratively slapped by reviewers, not sort of really someone coming out of nowhere and assaulting you. But to go through and say what I did is I just went through and looked at this with a series of pairwise tests for those types of things. Again, you'll lose some power on that, but again, I would make the argument, if your effect, whether or not it tips across p equal 0.05, depends on whether I look at it this way or this way. It's probably not a super reliable effect anyway. We want to make some caution when we're going through and interpreting anyway. So we'll go through some general sort of approaches, do some data work today, and then take things from there. Okay, got everybody's problem set 5 back. Really nice job with this. Really, it's kind of only minor stuff that you got dinged on. A couple things. Just want to make sure that you're thinking about sort of moving into this next set. When we're talking about confidence intervals, remember, for the purposes of this class, sort of my job is to know that you know kind of what this stuff is going on. And so sometimes your interpretations would be a little bit more elaborate than what you might put in for a paper or manuscript or something like that. But the one thing that I noticed is, through a lot of the interpretations, when we're talking about confidence intervals, remember that when we're running a test, what we're trying to do is get a point or some estimate of some actual real hypothetical value or effect or association out there in the universe, right? And so what we do is we collect a sample. We say, for my sample, this was the effect I found in my sample, or this was the mean difference on my sample. But my data would support population estimates ranging from here to here, right? And so in your interpretations of your confidence intervals, they were generally quite good. The only thing, just the thing that sort of noted on there, was just somewhere in there recognizing in your language so that you know that these are population-based estimates, right? So we're going from here to here. So my sample estimate doesn't range from this to this. My sample estimate is what my sample estimate is, right? But as an estimate of the population effect, that population effect, my data would support any value going from this to this in the larger population. And so some way, and you don't have to shotgun everything with population and throw that's not a good thing to do either. But just as you're writing up, sort of communicating that we're saying, hey, so this is my point estimate in these data, sort of my data would support population estimates ranging from this to this, or saying in the larger group of people with PTSD, or for the hypothetical population of all individuals who could be exposed to this manipulation, just something like that, just to kind of flesh this out, to let me know that you're talking about. Say, hey, out there in the world, these are kind of the range of values that my data would support. Okay. Other nuanced thing to think about that came up in a couple of things. Being careful not to conflate our effect sizes with our hypotheses testing. Okay, I can have a really, really massive effect size and have that effect size not be associated with data that come up as statistically significant, sort of using our conventional standards, right? Probably just means I have a really small sample. Same thing, I can have an ultra tiny, like small, probably not relevant or sort of practically meaningful effect size that's associated with a wildly small p-value, right? Probably just means I have a massive, huge, super huge sample, right? So, and when we're looking at confidence intervals around effect sizes, this is one of the, people will make arguments as a limitation of this. Confidence intervals around our effect sizes are actually going to be quite large. And so what we can run into are situations where I have my my hypothesis test tells me I have evidence for a non-zero difference, right? That something, my confidence bound for my mean difference or whatever doesn't contain zero. But if I went through and calculated confidence interval on my effect size, the effect size does contain zero, right? And so then it kind of feels like we've got sort of some conflicting information. Just know, and that remember, when we're calculating confidence intervals around our effect size, this is involving that non-central t distribution, and those tend to be quite large. Unless we have really large samples, probably our effect size, the confidence intervals around our effect sizes are going to be pretty wide. And some people will make an argument that says, well, then what's the point of even putting calculating confidence intervals around effect size, because they're so big anyway? Like, yeah, fair point, right? But what I think is important is sort of approaching our data with open eyes and recognizing that, hey, so I have evidence of, for, let's say, that RSA example, a pretty large effect. But based on the uncertainty of my data, like really my data would support something that would be actually a pretty small effect here. So just sort of being aware of kind of what's going on, right? So, and sort of being careful not to conflate sort of our confidence intervals on our effect size with our null hypotheses testing and stuff like that. Okay. Other thing too, real, and it is a sort of a minor thing, remembering that when we're interpreting our confidence intervals, right? Being careful, same thing with our, if we're looking at our confidence interval versus our test statistics. Say, if someone were to say, oh, we, based on my independent sample t-test, have evidence for group A being larger than group B, something like that, and then saying confidence interval provides additional evidence for that there is a difference. Well, confidence interval and your hypotheses test are the same thing. They're sort of using the same information. They're providing similar information because they have to, because they're the same thing, right? So similar when we're interpreting our effect size, what we wouldn't want to say is something along the lines of sort of point estimate of our effect says that we have a large effect. Confidence intervals confirm this, or something, language like that, because it makes it sound like the confidence interval is telling you something different than the point estimate. But for our confidence for our effect sizes, our point estimate has to be within that confidence interval, right? So the confidence interval is just giving us precision around that point estimate. So just being careful with your language. It's small stuff, but just wanting people to have a real clear understanding of this, because it just helps sort of make mistakes and sort of avoids you down the road sort of making sort of interpretations that might sort of just be a little bit off with stuff. Okay. Does anybody have questions about anything that came up on that last set? Again, you guys across the board did pretty good with stuff. It's just sort of minor things here and there. Feeling all right with that? Okay, cool. Any questions? I've had some correspondence with a couple of you about the ANOVA set. How's that going? Any concerns, snags, anything that you're running into there? Feeling good about this? Okay, cool.
Sorry,
yeah.
Can I ask you a question really quick?
Yeah.
I was just thinking about it. And I talked to CJ a little bit. I just want to be clear. On number one, we're gonna have to finagle some, aren't we?
Mm-hmm.
Okay. I just wanted to be sure. CJ was pointing me in the right direction, but okay, that sounds good.
With that problem, and again, sort of talked with sort of Natalie about this a little bit. What you want to say hi to everybody?
I will. Sorry.
So
they said something kind of weird that
okay. What's going on?
They said they were like, we have to pull the seal off this roof, and then he's like, then I have to redo their work, and he's like, would have been good to know. And I was like, well, I know my husband. He was pretty specific about how it has to be sealed, so I would like him to come talk to you. And he's like, well, I'm gonna do what I can do, and I was like, well, he's like, I have to like undo the roof people's thing and then do their work again for them.
Okay.
And I know there was something with the ceiling, right?
Yeah. How about this, guys? I'm sorry. We got folks working on our roof and things like that.
But it came without.
Yeah, the gutter people and roof people just surprised at your house and like call you at like 7:30 in the morning, and hey, we'll be there in a minute. So take. I'll be right back. All right, all. Thank you for your patience. We've got salty people who work with gutters. You say gutter people, and that sounds real bad. They're not gutter people. They're people who work on gutters and install gutters. But yeah, when you got two different crews doing different stuff, I think they like to crab about one another's stuff, and then it starts to become a concern about like, oh, is my roof going to fall in or what have you. So we're good to go. Thank you for being patient. In terms of that first problem, yes. So what I like about that problem is that it's requiring you to understand sort of where these variance components are coming from, right? And variance components just means differences, right? And sort of understanding sort of the pieces and parts. When we get into some of the stuff today, you'll start to see that depending on some things, my methodology, whether or not I have a balanced design, whether or not I have evidence of differences, violations of homogeneity of variance across my different cells, starts to impact the differences that I will make in terms of how to conduct follow-up tests, what types of effect sizes to use, and things along those lines. And so with this, liking this because it's sort of forcing you to think carefully about where these things are coming from. Now, the approach that you take, Brittany, to go through and calculating those will be different than what we did in class. You might have to start in a different place, kind of work backwards, say, what do I have, and then how do I go from there? Just sort of think carefully, focus more on the conceptual formulas than the computational formulas, the definitional formulas, and we'll go through today, sort of going through and talking about like what actual squared deviations are going on and this, that, and the other thing is going to be a better approach than trying to look at G's and T's and stuff because you don't have the raw data, you can't do that, right? But sort of understanding where these things are coming from gives you much more flexibility in terms of being able to reconstruct or approximate tests and statistics based on just summary data, which happens to me all the time, right? Want to find an effect for power analysis or something like that, or I'm interested whether or not these things are correlated or have some sort of an effect. Maybe that wasn't the researcher's intent. But based on what you've got, I can take this, I know what's going on, how these things are calculated. And so I can put these things together and then come up with sort of what I need to get out of that, even if it's not something that was included in sort of the results of things. So as a didactic, I think it's good from a practical standpoint. It's not something you'll probably have to do a lot, but just understanding. So the purpose is to understand kind of where that stuff is coming from. Okay. So work on it. If you have questions, let me know, and we'll get you moved forward with stuff. Okay. Any other questions with that ANOVA problem set? Okay, cool. Thanks for getting in touch. Let me know if you feel like you're kind of beating your head into a wall. Sometimes it's just enough to say, hey, look at this direction versus that one, and then all of a sudden things start snapping into place. So, cool. All right. So we'll jump into our kind of where we left off last time, talking about these factorial designs. So we had introduced this idea of, with our one-way ANOVA, right, we just have one categorical variable, one categorical IV predictor, where we're looking at differences in groups on some factor across some outcome, right? But that's limited, and sometimes it turns out that human behavior is complicated. Maybe there are other things and other factors that we want to go through and include. And this is where our factorial ANOVA designs start to come in. So we had talked about here, remember, we're looking at the influence not just of temperature on performance, but also humidity on performance. I saw someone had mentioned last time, like, said, is there not a humid place in Texas? I don't know. I thought, like, Texas, like, there are parts of Texas that are like big ass deserts, right? Like, it's just like super dry. Not really. There's a whole thing. I don't know. I was there once. It freaked me out. I didn't care for it, and so I haven't been back. Anyway, though, so thinking about the combination of humidity and temperature on performance, right? And so thinking about here, we've got two factors. We've got humidity, which is we'll call our factor A, although it doesn't have to be, but we'll just do it because why not? So we've got 2 levels to our factor A, 3 levels to our factor B, and what we're doing is then looking at both the main effective factor A on outcome, the main effective factor B on outcome, and then whether or not, above and beyond the main effective factor A and factor B, whether or not the specific combinations of A and B start to influence performance on this. Okay. So again, remembering as these designs, wanting to be careful, it starts to become really, really easy to get really, really complicated designs, right? Like, oh, I've got 5 different factors that I want to account for. Each of them has 2 or 3 different levels to it. These will get out of control real fast, right? So even this is a fairly simple 2x3 design. We're talking about 6 distinct populations, right? We've got performance in 70-degree low humidity, 80-degree low humidity, 90-degree low humidity, and 70-degree high humidity, 80-degree high humidity, 90-degree high humidity. So we've got a lot of different distinct hypothetical populations here that we're dealing with. So just wanting to be careful as you're moving forward with your research to make sure that you're managing the size of this design. Okay. We talked about main effects of humidity, right, which we're seeing here in the margins. We're talking about main effects of temperature, which are going on down here in the margins. And again, saying, ignoring temperature, do we see differences across low and high humidity, right? And then ignoring temperature, ignoring humidity, are we seeing difference across 70, 80, and 90 degrees temperature, right? So these are our main effects, right? But then what we're looking at also with this these designs, and what we're often doing these, is to look at these interactions, okay? When we're talking about interactive effects, we're talking about conditional effects. Because what it means is the main effect, or the effective factor A on my outcome, is dependent on the second factor, okay? The idea being that if I don't know what level of the second factor we're talking about, I can't tell you what the impact of my first factor is, okay? And so we looked at this humidity table here, right? And so here we're seeing what we might call a main effective humidity, where people are performing higher in low humidity than high humidity. Then we have an impact of temperature, where we're seeing linearly, we're seeing decreases in performance as the temperature starts to increase, right? But if we look for an interaction in this, there doesn't look like there's much going on, right? So at low humidity, we're seeing a 5-point reduction as the temperature increases. At high humidity, we're seeing a 5-point reduction in performance as temperature increases. At each temperature across low and high levels of humidity, we're seeing the same 10-point decrease, right? And so in this example, my main effects are pretty much taking care of whatever's going on in there. There's nothing else really interesting or exciting, okay? But if we switch this around and still get the same main effects, right? We've still got a 10-point difference across low and high humidity. We've still got a 5-point decrease as temperature increases, but we've got something very different going on within our cells, okay? Here, what we're seeing at low humidity, temperature appears to have no impact at all, right? If humidity is low, doesn't matter if I'm 70, 80, 90 degrees, everything's staying the same, right? But if I go down through and I crank the humidity up, now all of a sudden I'm seeing an effect. I'm getting a 10-point reduction as the temperature increases at high levels of humidity, suggesting that there's more going on across these cells than what is being caught across these main effects. Okay, and this is where we finished last time, talking about this starts to become very easy to see if we're presenting things graphically. Okay, so here is our first example. This one. Okay, we're seeing that as temperature increases, performance decreases, both for low and high humidity. It's decreasing the same at each level, at each temperature level. The difference between low and high humidity is the same. Everything's staying even Steven. We've got these parallel graphs suggesting that there's no interactive effects here. Okay, but if we look at the second example that we worked through, now we've got something different going on. The effect of temperature on performance differs depending on whether or not we're talking about someone working in low humidity or high humidity, right? Whether in Wyoming or Texas, temperature impacts performance. If I'm in Wyoming, temperature doesn't impact my performance because we got like negative humidity here, right? But if I'm in Texas, high humidity, what I start to see is decreasing performance with increasing heat, okay? And so same thing, so the thing that's tricky with these interaction terms, these interactions, they're sort of interchangeable, right? I can talk about this as the impact of humidity on the effect of temperature on outcome, or I can talk about this as the way in which temperature influences the association between humidity and outcome. We can do this either way, right? So here, probably the easiest way to talk about this would be the impact of humidity on the relationship between temperature and performance, right? For people at low humidity, temperature has no impact on performance. At high humidity, temperature definitely has an impact on performance, right? But we could switch this around and talk about the impact of temperature on the relation between humidity and outcome, right? Here at 70 degrees, humidity doesn't have an impact. At 80 degrees, looks like temperature has a little bit, or humidity has a little bit of an impact. 90 degrees, humidity really has an impact. Either way we want to talk about this is going to be a conceptual decision, and sort of based on how you've set up this problem, okay? And we'll get into more about sort of going through in some of the interpretations, okay? Similarly, if we have other types of interactions here, right, this is all kind of a linear pattern, which is fine and easy, but we can have other types of things, right? So here, no interactions, we've essentially got parallel line plots, okay? Here, we're seeing clear interactions because we have divergence across these means. So our line plots are a nice way, they're an easy way to go through and very quickly detect to see if we have interactions. Problem is that sort of these line plots sometimes aren't the most intuitive way to present group-based analyses necessarily. We'll often see these presented as bar plots. So here is a bar graph of sort of this same effect, right? But what we're seeing here is that about the same difference for low humidity versus high humidity at 70, 80, 90 degrees, right? We're seeing a decrease in performance at low humidity, or at high humidity. We're seeing a decrease in performance at low humidity, right? So this is the bar graph representations indicating that we have no evidence of an interaction here. If you want to, what you can do, if it makes it easier to see this, if you draw a point at the top one, at the top center of each one of these bars, and then draw a line through here and draw a line through here, you're basically back to what you've got here, right? So just saying that we don't have an interaction, okay? Here, what we have is our interaction. Here we're looking at, in our first graph, the simple effect of factor A at B1 is the same at B2 and B3, okay? So the simple effect of humidity on performance is the same at B1, B2, B3. We got the same difference between low and high humidity, okay? But here we have an interaction where the simple effect of factor A differs across levels of factor B. So again, factor A is humidity. Simple effect of factor A, do we have high and low, or differences in high and low humidity? At 70 degrees, no differences on high and low humidity. At 80 degrees, some difference. At 90 degrees, more difference. Okay. What we can also do is if we draw a point between each of our low humidity bars and our high humidity bars and draw a line through that, we get the same thing as we do here. Okay. It's just when we're talking about our group-based stuff visually, this is just an easier way to present this and something that makes a little bit more intuitive sense to people. Now, when we get into repeated, well, in the spring of 2020, if you all decide to sit in on and sort of just hang out and sort of take 5300, we'll talk about repeated measures designs. For repeated measures designs, these line graphs are often nice because you get the same people following over time. Gives you a sense of continuity. But with our completely between group designs, your bar graphs are probably going to be a better way to go through and present stuff. Okay. So questions on this. Okay. So here is the question within sort of these designs. Can or should we interpret main effects in the presence of reliable conditional effects? Okay. If I have an interaction, should I be interpreting main effects? So the question here is, in this case, let's see in this bottom panel here, this is a representation of these data here. Okay, so no effect of temperature at low humidity, effective temperature at high humidity. But if I look at my main effects, so I have an interaction, but here I'm saying I have got a main effective humidity and a main effective temperature. Should I interpret main effects of temperature and humidity in the presence of this interaction? I don't know. What are your thoughts, or what have you heard maybe in previous labs research, anything like that? So the question is can I say, based on these data, that humidity impacts performance? Well, if I'm looking at my main effect, it looks like humidity impacts performance, right? But what's the problem with me saying humidity impacts performance? What do you think, Allie?
It's only impacting performance.
I'm sorry. Yeah, no, I had my volume turned down. What's that?
Oh, because it's only affecting performance at high temperatures, so it's not technically doing anything to performance at low temperatures.
Exactly, right? For this, I can say I've got a main effect of humidity, and my main effect of humidity says that people are performing better at low levels of humidity than high levels of humidity. But that's kind of an incomplete answer, and it's a little bit misleading, because at some temperature, humidity doesn't impact performance at all, right? But at other levels, at higher temperatures, it impacts it a great deal, right? And so the question is should we, same thing with temperature, right? You say, oh, my main effect says that performance systematically decreases with increasing temperature. Well, kind of, but that's not the whole story. At low levels of humidity, temperature doesn't have any impact on behavior, but at high levels of humidity, it does, right? And so the concern with asking, can we interpret main effects in the presence of a reliable conditional effect? Or sort of conditional effect just means interaction. Condition means dependent, right? If I have a conditional effect, it means this effect is dependent on some other factor, right? So I can't tell you what the effect of temperature on performance is unless I know what type of what humidity is looking like, and I can't tell you what the impact of humidity on performance is unless I know what temperature it is, right? And so people will say that you should not interpret main effects in the presence of an interaction, which is a generally reasonable guideline to go through and sort of talk about. But my stance on sort of rules of thumb and guidelines and things like that. We have to use our heads and think about things, right? And so let's say, let's say we have a different study, okay, that's looking at the impact of smoking on heart disease, okay? And so we're looking at smokers and non-smokers at young adulthood, middle adulthood, and old adulthood, right? In this example, we could easily see an interaction, right, where we see that advancing age is associated with heart disease, right? As we get older, we sort of have more vulnerable to heart disease, and that smoking is associated with increased risk of heart disease, but we get an interaction, right? Risk of heart disease for 20-year-old smokers is probably not huge, but at sort of mid-age, probably larger. At old age, maybe larger, right? And so the question is, there we have an interaction, right? We say the risk of heart disease, the impact of smoking on heart disease is dependent on age, right? But in this case, I would make an argument for making a broad interpretation of the main effect because it's kind of important. Say smoking is bad for you. Like smoking increases your level of heart disease, or your risk of heart disease, okay? Let's just get that out of the way, okay? We can also say that your relative risk of heart disease increases if you're for smoking as people advance in age. But sort of this main effect that smoking is bad for your health is still kind of an important thing, right? So it's more of an issue of question and sort of design and interpretation, right? I would say in general, if I have a evidence of an interaction effect, I should be very careful about sort of making broad sweeping interpretations of my main effects. But depending on what you're doing and what the sort of the nature of your question and sort of what your data are looking like, I can see making arguments for interpreting those main effects, so long as we recognize that these are no longer main effects, these are conditional effects, because the impact of smoking on heart disease is conditioned on age, right, or dependent on age, or the impact of temperature on performance is conditioned on humidity levels, right? So just thinking very carefully about sort of what my data are saying, how do I go through and approach this, and how do I go through and interpret things in a way that's clear and communicate some of the nuance starts to become important. Questions about this? Okay. Other thing that happens too is sometimes you'll hear people say, well, you can't interpret an interaction, you can't interpret an interaction if you don't have any main effects. Okay. This is misguided. This will come up. It's absolutely not true. Okay. What we see with these designs is our main effects and our interactions are dependent of one another. Okay. Whether or not I have an interaction effect has nothing to do with whether or not I have main effects. In fact, what we can do is have situations where we have a clear interaction effect in the absence of main effects. This is actually kind of an interesting thing, right? So example here, we're seeing that in this 2x2 design, right, we've got a main effect of factor A only. Okay. Differences across factor B, not there. Sort of level, we're getting same impact or same outcome scores across both levels of factor B, but here we're seeing a main effect of factor A. Level 1 is scoring higher than level 2, collapsing across B, but no interactions, right? So at level, at A1, B1 and B2 are equal. At A2, B1 and B2 are equal. At B1, A1 is 10 points higher than A2. At B2, A1 is 10 points higher than A2. So no interactions, just a main effect of factor A alone. Okay, people seeing this? Okay. Here, we've got a scenario where we're seeing main effects of both factor A and factor B. Okay. We're seeing in our margins here, we're getting a 10-point increase from A1 to A2. We've got a 20-point increase from B1 to B2, right? And if we look at our cells, so we've got a main effect here of A, got a main effect of B. But if we look at our cells, we really don't have any evidence of an interaction, right? At A1, we've got a 20-point difference between B1 and B2. At A2, same 20-point difference between B1 and B2. At B1, A2 is 10 points higher than A1. At B2, A2 is 10 points higher than A1, so no interactions here. But we do have two main effects. People see this? here we've got a case, which would be similar to the situation I had indicated, where we have an interaction with no main effects. Okay, here, collapsing across B, A1 and A2 are identical. Collapsing across A, B1 and B2 are identical. So there's no main effects. If I were to just look at this and not look at the interaction, I would say A1 or A has no impact on outcome, B has no impact on outcome. There's nothing to see here, right? But if I go through and I take a look at sort of what's going on in these cells, we've got something very different. We've got a crossed effect, right? At A1, we see a 10-point increase from B1 to B2, right? But at A2, we see a 10-point decrease from B1 to B2, right? At levels of, at B1, A1 is 10 points less than A2, but at B2, A1 is 10 points more than A2, okay? So what we're seeing here is a cross effect. These things cancel out, right? So we don't have a main effect, but we've got a very interesting interaction effect going on here, right? And so this is all getting at questions of moderation, okay? We talk about these as interactions in ANOVA, but basically what we're looking at is moderated effects, okay? A1 and B2, independent of one another, it doesn't look like anything's going on. So if I say, hey, are levels of B related to outcome? I would say no. Levels of A related to outcome? No. And if we keep doing this over and over again in the research, we say, there's nothing to see here, right? But if we put them together, what we start to see is that B ends up being a moderator of A. The relation of A, the differences in A1 and A2 with my outcome change across across levels of this other factor, right? And so this is where these designs start to become important, where we're starting to look at the conditional effects of A on my outcome at different levels of factor B, or conversely, sort of the differing effects of B on my outcome based on levels of factor A. Okay. All right. I see your eyes going up and sort of looking, sort of pondering this a little bit. That's exactly right. I mean, sort of, it takes a while when you're looking at this stuff for it to kind of lock in. But when it does, you're going to say, okay, I start to see what's going on. But it's important to think carefully and know how you're sort of what's going on in your data and how to go through and approach this, because it's going to make an impact on how you go through, run your follow-up tests to try and tease some of this stuff apart. Okay. Questions on this stuff here? Okay. So, just a summary of our effects with our two-factor ANOVA. Okay, two-factor ANOVA means I just have two IVs. Okay, what we have here, 3 different omnibus effects, each with their own hypotheses and inference tests. We've got a main effect of factor A. Okay, this is saying what's the impact of levels of A on my outcome, ignoring B. Right, we were pretending B is not even there. We're just saying, are we see differences in means across levels of A? We've also got a main effect of factor B. Ignoring factor A, are we seeing differences across levels of B? And then we've got an interaction effect. This is the combined effect of A times B. Okay, we're saying here that the influence of factor A is dependent on factor B. I can't tell you the impact of factor A unless I know what levels of factor B we're talking about. Or the influence of factor B depends on factor A. I can't tell you the impact of B on outcome unless I know levels of factor A. Okay, and this is where our interaction effects start to come in. Starts to greatly impact and sort of expand sort of our understanding of phenomena. Super interesting, but gets a little bit more complicated in how to tease this apart in a way that's easy to communicate and sort of let people know what's going on. Okay. All right. So, if I'm going to calculate this two-factor ANOVA, okay, if we're thinking about conceptually where our different pieces and parts of our analyses are coming from, I think sort of this graph is a nice way to envision things. Okay, if I'm talking about variability, and remember in ANOVA terms, when I'm talking about variability, that just means differences. That's code for differences. Okay. What I've got at the top is my total variability in my data, all the differences that are existing in my data at the very top. And what I'm going to do is I'm going to split that into 2 separate sections. I'm going to have my within treatment, or my within factor variability, and my between factor variability. Treatment, again, is just a traditional ANOVA term for manipulation, things along these lines. Okay, and so Erica, what do I call my within treatment variability in ANOVA? What does that represent?
Error?
Yeah, that's my error. That's all the stuff that's going on within each one of my cells. Within my cells, everybody should be the same, right? If my factors completely account for and determine my outcome, then everybody within a given cell should be exactly the same, identical. And if they're not, that's stuff that's not accounted for in my model. And anything that's not accounted for my model explicitly is error, right? And so some of that might be random error, just sort of random fluctuation, stuff like that. Could be systematic error. It could be some factor that I'm not accounting for that probably should be driving differences. But anything that's not explicitly modeled in my analyses is error, okay? And Natalie, what about the between treatment variability? What's that represent?
Like any effects that are occurring?
Yeah. Probably some smattering of sort of random error, but then also some of those systematic effects. These are the differences in my actual populations that exist out there in reality that are driving differences in scores across my groups. Okay. Now with our one-way ANOVA, this is all we did. We just had between and within. But with our factorial ANOVA, what we're going to do is we're going to take that between treatment variability and we're going to start to break it up into other areas, right? So of the differences that we're seeing that are likely due to systematic differences, how much of that is attributable to factor A, how much of that is attributable to factor B, and how much of this is attributable to this interaction. The combination of differences within cells that's not accounted for or captured by my main effect of A and B here. Okay, so if you're thinking about how we're going through and putting this together, use this as kind of a map to think, okay, this is where my stuff is going. This starts to become important when you start doing more nuanced and complex stuff with effect sizes, with contrasts and things like that, being able to look at your ANOVA table and know where these different variance components are coming from so that you can sort of go through and do wonderful, interesting magic as we sort of get into more complex stuff. All right. So going to go through and talk about, sort of as we did before, where in our ANOVA tables for our factorial design, and this is a table for a two-factor ANOVA, sort of where our stuff is coming from. Okay. So here we're going to have our main effective factor A, we're going to have our main effective factor B, we're going to have our interaction term, and then what we're going to do is we're going to have our errors and our total. Okay, so we're just basically doing the same thing that we did with our one-way ANOVA in terms of piecing this out, but all we're doing is then taking that between group between treatment variability and factoring it out into different components. Okay, so if you pull up your handout here that I sent. So here what we're looking at is, let's say we've got, for this example, we're dealing with a hypothetical situation where what we're interested in is looking at the impact of, let's say, arousal and task difficulty on performance. Okay, and this is something that sort of it's kind of that inverted U shape. Like, so what is the impact on the difficulty of a task and sort of my level of activation, arousal, engagement on things? The idea that being like, maybe there's some optimal level of arousal, right? If I'm too low, that's not good on performance. If I'm too high, that's no good. If I'm dead center in the middle, that's probably where I want to be. But does that differ across tasks that are quite easy versus tasks that are difficult? Okay, so we have a small sort of demonstration set here that we're going to use as we're going through this our table here with things. Okay, so in terms of thinking about calculating our effects and where our components are coming from, I'm going to start out here with thinking about our sum of scores total. This is the total variability for our entire set of scores. Okay, and remember, sum of squares, variance, standard deviation, these are all just different iterations and manifestations of the same exact thing. It's just variations in our data. Okay, total variability, we get this the same way as we got it with a one-way design. We've got so, Erica, felines love statistics. It's a known fact. All right. So our sum of squares total, this is just going to be the sum of the squared deviations of our individual scores from the grand mean. Okay. Don't get thrown off by the notation. I just means person. J is factor 1. K is factor 2. And so what we have here is that our sum of squares total is just the sum of the squared deviations of person I at level J of factor A and K in factor B minus the grand mean. And then that squared. So in our example, our our total sum of squares total is just going to be the sum of the squared deviations of 3 minus 4 squared, plus 1 minus 4 squared, plus 1 minus 4 squared, plus 6 minus 4 squared, plus 4 minus 4 squared, 2 minus 4 squared, 5 minus 4 squared, so on and so forth. Okay? This is just all the variability in your data. If you were to take whatever your outcome is and just calculate the variance of it, that's what this is going to be. This is the total piece of the pie. This is all the variability in the sample that we have to work with. Okay? This is our total that we're then going to through our ANOVA, split into our within group stuff, or our error, and our between group stuff that starts to tease out our effects. Okay? So thinking about this, your total variability in our ANOVA is just going to be definitionally the sum of the squared deviations of every individual score from the overall sample mean. Okay. Again, we're going to split this out. Degrees of freedom is just going to be the total number of people in our sample minus 1. Okay. And so if you take a look at that handout that I provided there, you could calculate it this way. That would take some time. You can use summary statistics to do it. This is a computational formula. The sum of your x squareds minus the grand total over squared over n. So if we go through and we do that based on your handout that you've got, this is 840 minus 120 squared over 30. Degrees of freedom, total number of people in my sample minus 1. That gives me my total variability and corresponding degrees of freedom. Okay. Ari, if I took 360 and divided by 29, what do I get? Conceptually, you don't have to do the math.
It's total variability.
Yep, it is total variability, but more specifically variance. Remember, our variance is just the sum of squares divided by the degrees of freedom, right? And so if you were to do this, what you would get the same number as if you just said, I want to look at variability or calculate my variance estimate from everything, right? So this is just going to give you total variance in the sample. Okay. All right. And then what we're going to do is we're going to switch over. We're going to calculate our sum of squares error. Okay. Here, just as Erica indicated, sum of squares error is the variability within each condition or group. Okay. What we're doing here is our sum of squares error is the sum of the squared deviations of person I in, person K at level I of factor A and J of factor B minus their respective cell means. Okay. So again, if I'm taking a look at my handout here, right, what I'm doing, and if we think about what's our sum of squares error is, this starts to make some sense, right? What it is, I'm taking 3 minus 3, square that, plus 1 minus 3 squared, plus 1 minus 3 squared, plus 6 minus 3 squared, 4 minus 3 squared. That's giving my sum of squares for that group, plus 2 minus 6 squared, plus 5 minus 6 squared, plus 9 minus 6 squared, 7 minus 6 squared, 7 minus 6 squared, plus 9 minus 9 squared, 9 minus 9 squared. So what we're doing is we're going through and we're taking each individual person, looking at the square deviation of their score from the cell mean, and then adding all those up. Okay, and so what we're getting here is variability within cells, how far people are differing from their respective cell means, right? And remember, if factor A, if task difficulty and arousal level 100% determined my performance, then everybody in this group should be identical in terms of their scores. Everybody in this group should be identical in their scores, right? But there's not. That means there's either individual differerences or factors that we're not accounting for. We're seeing variability within our cells, suggesting that there's some error in that there are things going on that aren't accounted for by our data. Okay. People see where we're getting our sum of squares errors. Okay. Computationally, we can take a shortcut here, and we can just take the sum of squares for this group plus 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 this group gives us the same thing, right? A little bit of a shortcut in these data. We can also get our sum of squares error by subtraction. Okay, if we take the sum of squares total and we subtract sum of squares cells, which we haven't talked about yet, again, if we're thinking about total as the total piece of the pie, right, and we want to get a component, what we can do, sum of squares cells is just basically all of the between groups variability in the data. So if I take the total minus the stuff that's between, what I'm left with is just error. Okay, so our degrees of freedom for our sum of squares error is going to be the product of levels of factor A, levels of factor B, and the number of participants per cell minus 1. So basically what we've got is A times B times n minus 1 for a balanced design. We can also get my degrees of freedom by subtraction based on sort of what's going on in my table here. Okay, take degrees of freedom total minus degrees of freedom A, degrees of freedom B, AB, and we've got it there. Questions about this? Okay, so remembering that our sum of squares error, this is just the variability within our cells that's due to individual differences and experimental error and sort of factors things that we just haven't counted for. All right, so if we want to do this, so based on your handout, do this really quickly. We just add the sum of squares within each group, right? So we got sum of squares from easy low, medium low, or excuse me, easy low, easy medium, easy high, plus hard low, hard medium, hard high. Add those all together. That gives us our sum of squares error. Degrees of freedom errors, A times B. So we got 2 levels of factor A, 3 levels of factor B. Got 5 people in each cell. Gives us our error, or our degrees of freedom error here. All right. Now, what we're going to do is take a look at our sum of squares for factor A. Okay. What we've got here is our sum of squares for factor A is the variability or our differences. Remember, the variability is just ANOVA for differences across our levels of factor A. Okay. And so what we've got is, to get this, we've got the sum of our squared deviations of mean level of the mean of level I of factor A from the grand mean multiplied by the cell size and the levels of factor B. Okay. Again, this is assuming a balanced design, but essentially what we're doing to get our sum of squares for factor A, right? What we're going to do if factor A is, what do we say factor A is? Okay. Factor A here is arousal level. Okay. And so what we've got here is we've got the mean for low arousal, ignoring task difficulty. Down here we've got the mean performance for medium arousal, ignoring task difficulty. And here we have the mean of high arousal, ignoring task difficulty, right? So if I'm looking for my sum of squares for my factor A, it's going to be 2 minus 4 squared plus 5 minus 4 squared plus 5 minus 4 squared, right? So we're looking at differences across our overall average for levels of that factor, ignoring other stuff, okay? And then we take that, multiply that by the number of levels and sort of the number of people in each level. And so if we do that, you'll see we end up with, we were going to do this by our computational formula. We've got 90, sorry, I got turned around. I guess we've got 2 levels of factor A. I've got task difficulty is factor A. Okay, so for this, it's going to be conceptually 6 minus 4 squared plus 2 minus 4 squared. We're just looking at differences across easy versus hard tasks. Okay, so here we've got our row total, 90 squared divided by the number of people in our sample, 15, plus 30 squared over 15 minus 120 squared over 30. The degrees of freedom are the number of levels of factor A minus 1. So it gives us 1 there. So factor A, 120 minus 1. Or excuse me, 120 for my sum of squares, degree of freedom 1. Okay, and then same thing for factor B. We're just looking at mean levels of each level of factor B, collapsing across A minus the grand mean times the number of people in the cell times the levels of the factor. That should be factor B, not factor A, but you get the idea. So again, this is where we're going to go 2 minus 4 squared, 5 minus 4 squared, 5 minus 4 squared. So just looking at those differences, collapsing across task difficulty, just looking at performance at low, medium, and high. And so if I do that, again, using the same formula here, I have 20 squared over 10, 50 squared over 10, 50 squared over 10, again, minus the square of my grand total over the total number of people in my sample, right? Again, I've got 3 levels to factor B, so 3 minus 1, which is going to give me 60 for my sum of squares, 2 degrees of freedom. I'm good there.
Can I ask a question?
Yeah.
I'm understanding like where you're getting these numbers from. I just want to clarify for myself. So this 20 squared, are you doing what you're talking about? Is that where the 20 comes from?
Yeah. So
like, on this chart.
Yeah. So what I want you to focus on are the definitional formulas, the conceptual formula. Okay.
Okay.
This is just numbers. Like these mathematically are the same thing. This carries meaning in terms of conceptually what this actually is. This is a mathematical shortcut that gets you there. Okay. For the purposes of this, the mathematical shortcut is just easier to go through and do it if you have access to raw data. And probably in your lifetime, you'll probably never actually grind out a factorial ANOVA by hand.
Yeah.
But what I want you to do is understand very clearly where these different variance components are coming from and what they mean. And so that's why we're going through. This is always kind of a controversial thing in statistics. Like, oh, should I force you all to sit here and work through a factorial ANOVA by hand? Well, are you ever going to do that? Beck, no, probably not. I don't know. Maybe you're stuck on a shipwrecked on an island and want to crank out to maybe you're doing some stuff. I don't know, crabs and coconuts and things. Keep yourself busy. But in general, you're going to have access to statistical software that'll do this for you. But what's important is knowing where these come from, because then that's going to open up sort of your flexibility for sort of interpreting or saying if things are going wacky.
So where does T2 come from then? Like column, like T2 column. Where is that on this?
Yeah, it's right here. Right, so this is just the total of your column.
Oh.
If I add up all my scores within this column, if I add up all my scores here, this is what I get, right? T's are just totals. Okay. And these ones this is just the total of everybody in this cell, total of everybody in this cell, total of everybody in this cell.
Okay.
You got it?
Yeah, that makes more sense. I just didn't know how you were getting that number, but you're just adding them up. Okay,
Yep.
That makes sense.
Okay. All right. So we've got our main effects. We've got our total. We've got our error. Now what we need to do is start thinking about how do we tease out sort of the variability or the variance that's attributable to individual differences across these cells. Okay. And so from a computational standpoint, what we're going to do is we're going to calculate something called sum of squares cells. Okay. And your sum of squares cells is going to be the differences or the variability across all your individual cell means, right? Typically don't see this in your standard ANOVA table, like the one we have here. You do get this in SPSS. You'll see it under, it's labeled corrected model. Basically, this is like your sum of squares for all your different cells, okay? So if we wanted to get a variance component that captured differences across all of your individual cells as if you were running it like a one-way ANOVA, this is kind of what's going on, okay? And this sum of squares between is going to capture systematic differences across levels of factor A, systematic differences across level of factor B, and then systematic differences associated with the combination of A and B. Okay, so this is kind of your big sort of chunk, right? So your sum of squares cell is this piece right here. It's the between group variability. So if we've been following along, we've calculated total variability, we've calculated within treatment variability, we've calculated factor A, we've calculated factor B. Now what we're doing is we're calculating all of this here. And this is your sum of squares cells. Okay. And so if we do this, okay, sum of squares cells is just going to be literally the sum of the squared deviations of your cell mean minus your grand mean times the number of people you have in each cell. Okay. Or what we can do is we can get this by subtraction by taking your sum of squares total, subtracting your sum of squares error. That's going to give you your sum of squares cells. Okay. So again, if I take this and I subtract this, I'm just left with this, right? But conceptually what we've got is the sum of the squared deviations of your cell means minus the grand mean. Okay. So here, what we do is our sum of squares cells is our sum of squares total minus our sum of squares error. So like 360 minus 120. It gives me my my value here for my sum of squares cells. I guess I didn't put that down there, but 360 minus 120, 240, that's what you're going to get here. But this isn't, there's no place for it in our standard table here. This is just kind of a computational figure that we're sort of putting out to this side. So what we can do now is then calculate our sum of squares for our interaction, our AB interaction. Sum of squares AB, this is the variability due to the combined effects of A and B, right? Always get this by subtraction. This is easy. We're just going to take sum of squares AB. This is going to be your sum of squares cells minus sum of squares A minus sum of squares B. Whatever's left over, that's your interaction, okay? And again, if we think about our figure here, right, we've got our sum of squares cells. This is all the variability here. And if we go through and we subtract A, subtract B, the only thing that's left in there is due to my interaction. Okay, so if factor A and factor B completely count for everything that we've got going on, there's not much left for that interaction, and so that we're probably not going to get an effect there. But if we take all of the between group variability and we pull out factor A and we pull out factor B, and there's still quite a bit left over, that's suggesting that there could be some interaction thing going on here. Okay, so our degrees of freedom are going to be the product of degrees of freedom A, degrees of freedom B. So here we've got 240, which was our sum of squares cells that we calculated off screen, minus 120 is my within, minus 60 is factor A, or excuse me, we take 360 minus factor A, 120 minus 60 minus factor B, and what we're left over with is going down here. So we've got, for my interaction, got a sum of squares of 60. My degrees of freedom, 1 times 2 is 2. Got that there. And now what we've done is we've gone through and filled in my sum of squares covariance components for each one of these different effects. Then we know that if I got my sum of squares and I've got a degrees of freedom, then all I need to do is go through and divide my sum of squares by my degrees of freedom, and that gives me a mean squared. Allie, what's mean squared code for in ANOVA language?
Mean squared. Sorry, I'm blanking. I don't know.
What do I, if I take a sum of squares and I divide it by a degree of freedom, what do I get? What statistic does that give me?
The difference? Sorry, I don't know.
So if I take a sum of squares and if I divide the number of people in minus 1, what does that give me?
Sorry, I literally don't know. I'm like blanking. My head is
Yeah.
blank right now.
What statistic do we get from our sum of squares?
Like the effect, like the difference.
Yeah, we're gonna get an effect. Your variance?
Yeah.
Yeah. Like sort of like variance, like variance that we've.
Different.
Yeah. Okay. Oh, okay. I see what you're doing. You're sort of throwing some ANOVA back at me. Okay, gotcha. Yeah, in terms of variances as a measure of difference. But yeah, like so, what we did like in our one of our very first lectures, right? When we're talking about variance, and I take the square root of variance and I get a standard deviation estimate. That's what our mean squared error is. In ANOVA, mean squared is just a variance, right? So we have variance in factor A, variance in factor B. Here's our error variance, variance of our interaction. And the variance, my within treatment, or my error variance here. Okay, so mean squared just means variance, right? So this is the same variance that we use in our pooled variances and sort of with to calculate our t-tests and things along those lines, right? All mean squared is a variance estimate, right? So it gets a little bit confusing because we talk about variability as sort of our broad umbrella term for sort of differences, right? So sum of squares is a measure of variability. Variance is a measure of variability. Standard deviation is a measure of variability. Range is a measure of variability. So these are all measures of sort of the extent to which things sort of spread out or differ, right? But if I'm going through and talking about variance specifically, right, this is where I can take and will be relevant for the work that you're doing in this problem set. I can take a standard deviation, and from that standard deviation, I can get variance. From that variance, I can get a sum of squares, right? I can work back and forth between. They're all the same thing. They're just different metrics. They're just different forms of the same thing. Okay. So here, what we've done is we've got a sum of squares. We take a sum of squares divided by aggregate degrees of freedom. We get a variance estimate. In ANOVA, we call this mean squared. And then what I can do is then I can start to calculate my F statistics, right? I'm just taking my mean squared divided by my error. Mean squared divided by my error. Mean squared divided by my error gives me an F test for factor A, an F test for factor B, and then an F test for my interaction. All right. Questions about where we got this material from? Okay. So when you're thinking about this, thinking about for our omnibus tests in ANOVA, we end up with a significant, so for this, and if we went through and took a look at my p-values for 24 with 100, for my F, if I'm going through, let's see. Bring this in. If I've got here, squeeze that down some. All right. So I've got an F test of 24 with 2 degrees in the numerator and 5 degrees in the denominator. Or excuse me, no. 2 and 24 degrees error in compute. That's sort of massively small p-value. Okay. Same thing if I go F of 6 with or excuse me, that should have been 1 degree of freedom in the numerator, but 2 and 24, calculate p-value, 0.0077, right? So again, our f-tests are going to be degrees of freedom associated with my test over degrees of freedom error. That's the degrees of freedom for my f-tests. So we have in this a clear effect of evidence for a main effect of factor A, clear evidence for a main effect of factor B, and then we have our evidence for our interaction effect. Okay, and what this means then is that I no longer have a main effect of factor A. My main effect of factor A is a conditional effect, because the effect of differences in task difficulty on performance depends on arousal level, right? And my main effect, what I would normally call a main effect of factor B, that's now a conditional effect, right? Because the impact of arousal on performance depends on task difficulty. This interaction says that these two things are interdependent of one another, okay? And so in this case, what we would most likely do, unless we have a good reason to make some sort of general conclusion about the main effect of A and the main effect of B, is we would ignore what's going on here and just jump right into this interaction effect so we can start teasing out and talking about what's happening here. Okay. And so if I was going through and just doing a very quick interpretation of this, I would say evidence of my interaction in these data suggests that effective arousal on performance is conditioned on test difficulty. Okay, and again, condition just means dependent. And then anytime, so turn up your ears on this. Anytime you get a significant interaction effect, if you have evidence for an interaction, very first thing you want to do is plot this out. Okay, visually plot it out. The first thing you do nothing other than directly going into Excel or something along those lines and plot out these means to see exactly what's happening. Okay, because the interpretation of this stuff starts to get pretty tricky. What we always want to do is plot this stuff out before we rush forward and try and make any sense of it. I can say, just if I see that there's interaction, I note that the effect of factor A on my outcome is conditioned or dependent on factor B. But what that actually looks like, I don't know until I plot this out and hopefully have a game plan for how we go through and start teasing things apart. Okay. All right. Questions about any of this that we've gotten to up to this point? Kind of making sense-ish? Okay. We'll go through, we'll start working through some examples and go through some screening and stuff like that. But let's go through, take 10, let's come back at 3:37, just a little before, 3:37, 3:38, something like that. Come back, take 10, and we'll jump back in, finish up stuff, and then run into some data stuff. Cool. All right, folks, we're in the final stretch. How are we feeling? Any questions about ANOVA stuff? You know what? I'm worried about the temperature in your respective homes. There's a lot of blankets and cover-ups. Like, are you has your heat gotten turned off? Like, we got a lot of wood. I can bring fireplace. Like, I don't know, we could build a small fire in your apartments if you have no heat. Okay. Let me know if you need emergency services. All right. Cool. No one's going to die of exposure in their homes, which makes me happy. Going to jump back into ANOVA. You bathe in the warmth of factorial designs. This sort of cold, comforting arms. All right. Talk about our omnibus tests. Going to go through, this is general model. The different way of thinking about things. Again, this is just a GLM, like linear model approach to things, thinking about the prediction of the score for person I, for person K at level I of factor A and J of factor B is associated with some sort of grand mean where we start out with plus an adjustment for the level of factor A, plus adjustment for factor B, plus the interaction, plus some error term for them. This will start to become more relevant. And again, if you all decide to sit in on 5300, not this coming spring, but the following spring, we start talking about doing similar analyses within a context of a regression, this starts to become more relevant. But this is just sort of kind of a preview here. Okay. One thing we want to talk about real quickly is power. Okay. What we find is that our factorial designs are often more powerful than our one-way designs. And this increased power comes from the fact that what we do with our factorial designs is we start to shrink down systematic variability in the level of error variability in my outcome. Okay, and we're thinking about the types of behaviors that we're generally interested in. They're complex. There's a lot of factors that go through and influence things. Okay, and so what we do is we start to increase the factors that we're looking at. We start to account for more of the variability in our outcome. And if I account for more variability in my outcome, the error variability decreases. And because the error variability is the denominator of all of my statistics, is that decreases, my test statistics tend to go up. Okay, so let's say, for example, I'm interested in looking at emotional arousal against calm to excited in response to fear, amusement, and anger eliciting stimuli. So I got 3 different videos, right? I've got a fear eliciting video, an amusement eliciting video, an anger eliciting video. Have people go through and watch each one of these, right? What we get is we have total variability in people's reported emotional arousal, right? And then we have the variability due to differences across my fear, anger, and amusement eliciting stimuli. And then everything else that's not attributable to sort of the differences across fear, amusement, and anger eliciting stimuli gets dropped into my error term. Okay. So this study 1 is my one-way ANOVA, right? I just have 3 levels of my factor. My factor is film, and I'm looking at the impact of film on arousal levels, right? But then maybe I go through and I run study 2. Study 2, I still have the same 3 videos, but this time I start thinking about some other stuff that might go into impacting this, right? So maybe instead of just saying, oh, I have my 3 different films, maybe participant sex has an impact. Maybe men and women respond to these film stimuli differently, right? For whatever reason. And so what I'm going to do is I'm actually going to include participant sex as a factor in my design, right? So now what I've done is I've gone from a one-way ANOVA to a two-way factorial ANOVA, where my conditions are film, or I have a film condition 1, 2, 3. Let's say we go biological sex, say sort of 1, 2 on that. But then I have the interaction, right? Because it's possible that sort of maybe for my fear eliciting stimuli, it doesn't matter, men and women respond similarly. But maybe for my amusement stimuli, maybe men and women do respond differently, right? Maybe for anger, they respond the same. But maybe sort of men are finding, sort of my male participants are finding things more sort of this amusement stimuli different in some way than women, right? And so what I've gotten here, Ari, in study 1, what happened to the variability that's due to participant sex? Where did that go in study 1 here?
This might be wrong, but wouldn't it just get kind of like lumped together in variability effect?
Okay. Well, it might, but sort of if I have a systematic effect of participant sex, right? And I'm not controlling, and I'm not accounting for that in study 1 because it's just looking at differences across film. If I'm seeing systematic variability in sex, where does that get? Is that something that I've accounted for in study 1?
No.
And so where does variability that we haven't accounted for, where does that go? So for our models, if I've got something that I haven't accounted for, what is that?
Sorry, I'm not sure.
Okay, so I've got systematic variability that's due strictly to my film condition, and then everything else is what? if I'm looking at study 1.
Error?
Yep.
Oh.
If I haven't accounted for it, it's error, right? Now, there may be, in that error term, there may be systematic variability due to sex. There may be systematic variability due to neuroticism. There may be systematic variability due to a lot of stuff. But if I haven't accounted for it in my model, that's all getting dumped in the error term, right? But in study 2, what I do is I specifically model sex. Is I say, okay, I'm going to look at differences across these 3 films, but I'm also going to look at differences in how men and women are responding to this, right? So this error variability that was potentially due to sex and the potential interaction of condition and sex, that gets pulled out, and I'm modeling that specifically, right? And so, Erica, what happens to my error term relative to study 1? It decreases, it gets smaller, right? This variability that I wasn't accounting for in this design is accounted for this design, and so my error variability, my sum of squares error, my mean squared error gets smaller, right? And my mean squared error is always in the denominator of my F statistic, and the denominator of my F statistic is getting smaller. What's happening to my F statistic, Rachel?
It's getting bigger?
Yep. Right? This ratio is just math, right? If I'm dividing something by a smaller number, I'm accounting for more things, so more factors that are impacting my outcome. And so what we see, then sort of my test gets stronger, right? And this is the idea behind analysis of covariance, right? What we want to do is we want to sort of account for more things. The more things that we do and account for, the better that we predict our outcome, the stronger our test is, because there's just less sort of variability that's not accounted for, shrinks down that error term, makes our tests more powerful. So in general, when we're looking at our ANOVA models, our factorial designs tend to be more powerful than our one-way ANOVAs, just because we're accounting for more of the variability, more of the differences in scores or whatever it is that we're looking at. Okay. So thinking about effect sizes, right? We've increased our design, and so we've increased the number of possible effects that we could go through and look at with this. Okay, so one option that we have is still our eta squared. Eta squared is just the sum of squares of our effect over our sum of squares total, just like it was in our one-way ANOVA. Okay, again, my eta squared is the total variance attributable to an effect for this sample. Remember that eta squared is a sample statistic. In the data that I'm looking at right now, this is the proportion of variability, of total variability in my outcome that's attributable to this specific effect. Okay, but as you remember, eta squared, positively biased estimate of the population effect, so we're a little bit worried there. And what we start to see is that our eta squared will start to systematically decrease with the number of effects in our design. Okay. So if I'm looking at a one-way ANOVA, right? Let's say I'm just going back to our example where we got film, right? So I look at it and I calculate my one-way ANOVA is my sum of squares effect over my sum of squares total for film, okay? But then if I go through and I then rerun this analysis as a 2x3 ANOVA, right? So I'm looking at the impact of film and sex and the interaction on my outcome. What I'm now going to have is that sum of squares effect is going to be, I'm going to have a sum of squares effect for factor A, sum of squares effect for factor B, and then my interaction, okay? And so what's going to happen is the sum of squares effect for film is probably going to start, unless everything's completely orthogonal, unless I've got a true experimental design where everything's randomly assigned and factor A is completely unrelated to factor B, is completely unrelated to factor C, what's going to happen is the variability that I used to get for factor A now starts to get sort of pulled off into other factors, right? So let's say for you clinical folks, let's say, Rachel, you're looking at functioning in people who have engaged in self-harm but haven't, and people who engage in self-harm and those who don't, right? So that's not an experimental factor. That's something that exists out in the world. Like you can't randomly assign people to self-harm or not, right? But then maybe you also want to look at the impact of, say, social anxiety, I don't know, on sort of whatever your outcome is, right? social anxiety and self-harm probably are not unrelated to one another, right? And so now all the variability that was attributable to self-harm, some of that's getting pulled out into this. And so my sum of squares from my factor starts to get smaller and smaller. And so what we'll start to see is that we have problems comparing directly our eta squared across studies with different designs, okay? Because depending on the additional number of factors I go through, the sum of squares for my effect start to get smaller and smaller systematically, particularly if those other factors are related to that factor. And so we start to run into problems. Not so much for experimental designs where everything's randomized, but in general, we start to have problems comparing eta squared across different designs, and that's kind of a problem. Okay. So what we have and what we'll see as generally for these factorial designs as your effect size is something we're going to call partial eta squared. Okay, partial eta squared indicates the proportion of residual variance unaccounted for by other factors. Okay, so what's going on is if I say have my film factor, right, and I'm going to calculate partial eta squared for here. What I have is my sum of squared for my condition, for my film factor, over sum of squared for my film condition plus my sum of squares error. Okay, sum of squares, my sum of squares for my factor of sex and my film by sex interaction, that gets pulled out. Here with eta squared, you're looking at sort of what's attributable to your factor over everything else. Eta squared says what we're looking at is the sum of squares attributable to your factor versus everything that's not already accounted for by other stuff. Okay, so what we do with eta squared, the denominator of or partial eta squared, is my residual variance. So if I take out the variability that's attributable to my sex factor and my sex by film interaction, what I'm left with is my sum of squares affected by film over sum of squares affected film plus everything else, or my error. And so what I get is it's a partial coefficient. Okay, it's harder to account. It's harder interpretively. It's a little bit more difficult. Thinking about this, if this is my total variability, total piece of the pie, okay, what I've got, let's say I've got a piece that's associated with film, and then I've got another piece that's associated with sex, and then I've got another piece here that's my interaction. Okay, now this probably isn't how this would work out because these are going to be overlapping to some extent, right? But what we're saying is if I've got my eta squared is film over everything, right? Okay. My partial eta squared is film over everything that's not already accounted for by sex and interaction. Okay, so what I've got is then let's say this is error over here. So what I've got here in my partial eta squared is my partial eta squared was film plus error. Okay. So looking at this, Natalie, which one of these has the smaller denominator?
I guess the partial.
The partial eta squared, right? Because what we're doing is what we're calculating with our eta squared is film over everything. Eta squared is kind of like an R squared value, right? It's like what proportion of the total variability is attributable to sort of this factor. Easy peasy, easy to interpret. Problem is, it's not. It's a hard statistic. It's kind of an apples and oranges thing, depending on how many sort of factors that we have, depending on the design. And so what we'll get with partial eta squared is saying what's if we take out variability that's already attributable and accounted for by other factors. If we take that and we pull it out, so the stuff that's associated with sex and interaction, we put that aside. With what's left over, what does film account for everything that's left over? This is our partial eta squared. Okay, and so what we can talk about this is partial eta squared is of the residual variability of the stuff that's left over after we account for sex and interaction. Of what's left over, how much of that is due to film? Okay, and so what ends up happening is as we sort of add in other factors, sort of my factor might shrink as we start to sort of get some overlap in here, but my denominator also shrinks too because I'm accounting for other things, right? So what we see with my partial eta squared is instead of the proportion of total variability that's accounted for, what we're seeing with the partial eta squared is after we pull out the stuff that we all are known stuff, we've already accounted for that. Of what's left over, how much is due to film, right? So we've got our sum of squares for our film over sum of squares film plus our sum of squares error. This is going to give me my partial eta squared. Questions about this? Okay, these partial coefficients are something that are going to come up as you start to get into regression stuff. And again, if you elect to sit in on 5300, talking a lot about sort of different sort of ways to go through and sort of look at partial stuff, it ends up being big in regression. ANOVA is just a special case of regression. It's the same exact thing. We just talk about it a little bit different. But this is kind of where these partial coefficients are coming in. Okay, so our partial eta squared is reflects the proportion of leftover variance that's not accounted for by other things in the model, right? It's helpful for comparing across studies with different numbers of factors, central to our calculation of power. Okay. Less meaningfully conceptually, or it's harder to talk about conceptually, and continues to be positively biased estimate of the population effect for the same reasons that eta squared are. But if we're going to go through and calculate power for a factorial ANOVA, partial eta squared is what we need to be talking about. Okay. Other statistic here is F. F is the formal statistic that you'll see used for power calculations, but F and partial eta squared have a direct relationship. So we just say F is going to be our partial eta squared, the square root of partial eta squared over 1 minus partial eta squared. That gives us F, right? Alternatively, partial eta squared is just F squared over 1 plus F squared. Okay, so for eta squared, partial eta squared, these are our benchmarks, our interpretive standpoints, benchmarks for small, medium, large, for F, small, medium, and large. So F has no interpretive value. It's just a statistic, but it's the statistic that goes into calculating your effect sizes, or excuse me, your power. And so don't worry about what F means. Just know what F is. Know how to interpret eta squared and partial eta squared. But just know that F is another thing that's out there in the universe. Okay. Questions? Okay. So going over, just like with our one way, we also have our omega statistics. Okay. Omega family of statistics, these again are preferred in terms of making estimates of our population effect. Remember that our sample statistics, our sample effect sizes, eta squared, and partial eta squared tend to be positively biased. Our omega squared statistics sort of have some correction for things that tend to be sort of better in a lot of ways. And so what we've got is these omega squared statistics also start to account for the different types of designs that we're using. Only drawback is that omega squared starts to assume that what we're dealing with are balanced or nearly balanced designs. Okay. and how we go through and calculate these omega squared statistics start to depend on sort of what the design looks like. Okay. In your HAL text, there's sort of a whole table on how to go through and calculate these things. So you can start to see omega squared and partial omega squared sort of being broken down into these different components here. Shortcut over here is we can start calculating omega squared and partial omega squared from our F statistics. Okay, so if we want to get omega squared in a factorial design, I can take my degrees of freedom for whatever effect I'm looking at times the F test for that effect minus 1 over degrees of freedom A times F for factor A minus 1 plus degrees of freedom B times F for factor B minus 1, so on and so forth for however many factors we have in there in the design. For my partial omega squared degrees of freedom of the effect times the F for whatever effect I'm looking at minus 1 over degrees of freedom of whatever effect I'm looking at times F for that effect minus 1 plus N. The notation and the superscripts and subscripts got all jacked up here. I'm not sure why, but sort of basically shortcut here is just going through and using my F statistics and degrees of freedom to go through and calculate the my omega squared statistics. Okay, and again, interpretive standards for omega squared are the same as my eta squared statistics. Okay, so again, the distinction between eta squared and omega squared family. Eta squared are nice to say for this set. This is what I'm saying. But if I'm wanting to sort of make a generalization to a population effect, I want to say, in general, I'm expecting sort of total variability in response, in arousal in response to this film stimuli. This is due to film. If I'm talking about sort of wanting to make population-based estimates, probably need to be using omega squared statistics. And they're just going to be a little bit smaller than, systematically smaller than your eta squared and partial eta squared. Again, just because we know that eta squared, partial eta squared are positively biased. Omega and omega partial omega squared are also positively biased. They're just less positively biased. Calculation of our effect sizes. Again, just going through using our non-centrality calculator here to get non-centrality parameters for upper and lower, to go through and calculate effects confidence bounds on effect size for partial eta squared. Here, again, Steiger is recommending calculation of 90% confidence intervals because we can't have less. You can't have less than 0. It's not like a balanced thing. The idea is to calculate 90% confidence intervals so everything gets switched around. But again, calculation is going to be the same as sort of how we went through and done this. We just go through, drop in our F statistic, degrees of freedom, ask for a 90% confidence bound, compute, gives me my lower and upper, take my lower and upper, back translate those into partial eta squareds, and then that's what gives me my confidence bounds. Okay. So, summary of this. Eta squared, eta squared, omega squared, these are interpreted as total variability attributable to the factor. All of my components, adding it all together is going to be equal to 1, right? Conservative estimate, and that it's probably going to be smaller than our partial coefficients. Partial eta squared, partial omega squared. This is a proportion of residual variability in our attributable to whatever factor it is after we pull out other stuff. So basically, I pull out everything that's known, everything I've already accounted for. Of whatever's left over, how much of that is attributable to the factor that I'm interested in. If I add up my partial eta squared or partial omega squared for all of my individual effects, it's not going to equal 1, just because I have differences in the calculation of these different ratios. Again, useful for comparing studies across different designs. I've asterisked this. As we start to get into repeated measure designs, then we get into a whole new ball of wax with stuff. But if I'm trying to say, let's say Allie ran a study that has, Allie's got like a 2x3 factorial ANOVA, and Natalie, you're running a 3x4 by 2 factorial ANOVA, and you're wanting to compare effect sizes across those two. Your partial coefficients are going to be better in terms of comparing across. And are partial statistics used to calculate power of effects, right? So if we're going to go through, calculate our power, G power is going to ask for F's. F's are just a derivation of partial eta squared. You just go through and do that. And again, just a screenshot of our G power. Here you're going to go through F. You're going to select fixed effects, special, main effects, and interactions for the types of stuff that we're looking at. Your G power is going to ask for an F test, right? If you go through and hit determine, you can just hit direct and just put in your partial eta squared and hit calculate, and it'll give you your F, transfer that over, right? Alpha level, power that you are interested in, the degrees of freedom for whatever effect that you're looking at, total number of groups, right? And then it'll go through and calculate things for you. Questions on any of this? All right. So let's get into some actual data, start playing around with this, okay? So in this example, what we've got is we're saying that investigators are interested in the impact of expressive regulation on physiological activation and subjective response to sort of valenced film stimuli, right? And what we're doing is we have individuals are randomized to view one or two affectively valenced films, right? So people are either watching a sad film or a humorous film. And what we're doing is we're telling people who are watching these films to either inhibit the expression of emotion or watch the film naturally, okay? Simple manipulation. People are randomized to either watch a happy or sad film, and we're just saying either to watch it naturally or shut down all expression emotion, all expression in response to this, right? But before we get to that point, what we want to do is we want to run a manipulation check, right? Because maybe our reviewers say, hey, well, you told people to not express their emotion, but maybe they did anyway. How do we know that instruction manipulation was actually effective, right? So luckily, what we did is that during this film, or during this study, we went through and videotaped everybody, right? So we had video stuff, and what we did is we went through and rated overall level of participant expression on a 1 to 5 scale. 1 being no expression at all, 5 being like sort of through the roof in terms of expression, okay? And so what we're expecting is that if my manipulation is worked correctly, I'm expecting that participants who I instructed to inhibit expression are going to evidence lower ratings of global expression than people who were allowed to express freely, okay? So for this study, I've got 2 factors. I've got film condition, right? Whether or not people watch happy film or sad film. I've got 2 instruction conditions, right? Either watch naturally or inhibit your expression. And then my outcome is sort of expressive behavior that I've gone through and measured, okay? People have questions about this? All right, so this starts to become important. I've talked with a number of you, so when you're going through and approaching these problems, spend some time with this setup and make sure that you're clear on sort of exactly what the question is, what is being proposed. It's going to make it a lot easier down the road with your interpretation so that you can go through and kind of tease out effects and things along these lines. So what we're going to do is let's pull up, get out of here, Zoom thing. Let's pull up our data that I sent out here. So what we've got here is we've got a 2x2 factorial design. Okay, so we've got factor A is film, happy, sad, 2 levels of that. Factor B, 2 levels, inhibit, sort of don't inhibit. 2x2 factorial design, fully crossed, people randomized to both conditions, so it's completely randomized design. Okay, and so what we're going to do here is pull up this is the worksheet that we'll go through. We're going to start by screening these data to kind of give you a feel for how we might approach this. So here, as we're working through this, you can follow along your 2x2 ANOVA screening worksheet here as we're setting things up. Okay. So for this design, the first thing we have to probably think about when we're screening for, first thing we want to do is go through and take a look at whether or not I have any missing data, right? So here I've got my participant number, I've got film condition, instruction condition, and then I've got a condition variable here. We'll talk about that. And then my level of global expression. So if I go down through and look at this, we can see my film condition. 0 is the sad film, 1 is the amusement film. Okay. I've got my express condition. 0 is express, 1 is inhibit. And then I've got this condition variable here. I've gone through and pre-made this already. What it is it just corresponds to my different cells. So I've got my sadness express, sadness inhibit, humor express, and humor inhibit. Okay, so these are the 4 cells in my design. Okay, and then here are my global expression ratings. Okay, so I want to go through and say, do I have any missing data for my film? Nope, that's an experimental variable that should be manipulated, that I shouldn't have that. No missing data there. And then for my outcome, this is my express condition. Okay, looks like I've got 3 people who I'm missing data for. Okay, and if I go down through 192 people, Ari, am I too concerned maybe about missing 3 people in 192 people?
No, not super concerned.
Probably not super concerned, right? Good data practice says I would probably want to go through and figure out what happened to those folks, but probably it's a experimental error, film stuff sort of went dead or something along those lines. So would want to go through for this. First thing I want to do is take a look at missing data. Okay, so it looks like I have 3 individuals with missing values. Okay, but what I also want to do is want to make note of what condition those people are in. Because if I go through and I start to see I have missing values, but they're all coming from one cell, then that starts to make me wonder sort of whether or not these are randomly gone or something along those lines. So I would say I'm missing 3 values, or global expression values for 3 individuals. My first person is a sadness express. Second person is sadness withhold. 1 is humor withhold. So we just want to go through and make sure that in my screener, I'm saying missing 3 values, right? So I'm going to have to get rid of those people, but this is, these are their participant numbers. This is what condition they're coming from, okay? Because if all 3 of those folks were from the same condition, then I might start to worry about what was going on there, things along these lines, okay? So here, I'm going to start by just nuking those folks. We'll get rid of those. Okay, and so now what I want to do is I'm going to go through and maybe I'm going to go to descriptives, and I want to look at my expression ratings. Okay, and maybe I just take a look at those. Oops, just independently, just to see if all my ratings are sort of in the right spot. So again, here I said ratings 1 to 5. I'm seeing my ratings are 1 to 5. That's good. In SPSS, if I wanted to just go through and sort those, right? 1 max, 5 minimum, cool, right? So no problems with weird scores of 0 or 6 or something like that where someone had something going on. So in terms of plausibility, looking good there, no problems. Okay. So my next task, I want to go through and I want to take a look at take a look at my distributions, right? But for my screening of my ANOVA stuff, Robert, what do I want to make sure? Can I just look at my distribution of global expression for the sample as a whole?
No, you need to look at it across conditions.
Okay, and how many distinct populations do I have in this set, Robert?
4.
Yeah, 4. Okay, and so this is the important thing. This is where people often get turned around in terms of their screening. From this set, I've got 4 distinct populations, right? So what I want to do is make sure that when I'm looking at this, I'm looking at the distributions within each one of my groups. Okay, and so what I'm going to do is I'm going to go to data. I'm going to go to split file. Okay, oops. And in my split file, what I'm going to do is I'm going to go down to this condition variable that I've already gone through and created a variable here that has just each one of my cells. And I'm going to go through and I'm going to say condition. Organize, compare by groups. Select condition, move that over, and hit paste. Okay. And so what this is going to do, I'm going to say what I'm going to do here is this is going to go through and split my file up so that I'm looking separately at people by individual condition. Okay, and so now I'm going to go through. I'm going to go to analyze descriptives. I'm looking at my expression rating, but this time I'm going to save standardized variables. Right, I'm going to options. I'm going to ask for skew kurtosis and hit continue there, and then we go ahead and hit paste. So now what I've done is I've gone through telling myself I'm looking at this, splitting the file, and then I'm looking at descriptives by my individual z-scores. Okay, so I'm going to go through, run this. Okay, this is what I get. So what we'll see is I've got descriptives for my SAD express, my SAD inhibit, humor express, humor inhibit across all 4 of these levels. Okay. And so if I'm looking at this, Erica, what am any sort of thoughts, reactions to the stuff that we're seeing here across these cells? Or across these different, across these different groups.
They have different sample sizes.
Okay, they do have different sample sizes. Are my deviations super terrible?
No.
Not too bad, right? And so here what we've got is we've got an experimental design where I've randomized people to each one of my conditions. Things are pretty even, Steven. They're not perfect, but they're pretty close. Right, so wanting to note that it's not completely balanced, but it's close. Anything else about those cell sizes that you're noticing, Erica?
No.
Are these, so as an experimental person, are these nice cell sizes?
Yeah.
Pretty good, right? So what I've got within each one of these is I've got a relatively sort of kind of balanced-ish design, right? It's not exactly, I've got a difference of 7 people from my lowest to my highest, right? So I want to take that into consideration. But I've got decent sized cells, right? And what this means is this starts to give me some robustness in terms of my screening, because my assumption is that my distribution of sample means is normal across my cells. Allie, what are the 2 conditions under what my distribution of sample means starts to become normal? Oh, yeah.
Sorry, I thought I was on mute or off mute. As your sample size increases and if the population is normal.
Yeah. Okay. So if my population is normal, that I'm pulling from is normal, or my sample size starts to get sort of reasonably large size, then I start to have less concerns. Even if my observed data are pretty skewed, distribution of sample means I can assume is going to be relatively normal. So here, this is nice because I got reasonably large sample sizes. So I'm not so concerned. I'm less concerned about my observed data than I am about sort of what the actual distribution looks like necessarily. Okay. Rachel, going down through and taking a look at these, is there anything else I need to be necessarily concerned about from a screening perspective here?
I don't see anything big. There's like a restricted range that on SAD inhibition, but I don't think that matters necessarily for the screening.
Yeah. Okay. Beautiful pickup. Absolutely. Sort of wanting to say, looks like for those individuals, their level of expression in that sadness, people watching the SAD film who were instructed to inhibit, looks like they hit there wasn't a whole lot of variability in terms of their expressive behavior. Definitely something to take a look at, right? But in terms of our skew and kurtosis levels, particularly given the sample size, there's not much that we're probably going to be too concerned about here, or things that are necessarily going to give us pause. Okay. Questions about sort of anything that we did here? Okay. So what we want to do, so we've got things are looking at least promising here. What I want to do now is I'm going to go back to my data, and I'm going to sort my data. Robert, what did that? Oh, never mind. You're not an SPSS user. Rachel, what did that do to by sorting my data? What did that just do in SPSS? You know.
Did it unsplit the file?
Yeah, it took that split away, right? So I don't have to worry about it. Because what I'm going to do now is I'm going to go to Analyze, I'm going to go to Descriptives, and I'm going to go down to Explore. Okay, and what I'm going to do is I'm going to ask for expression rating as my outcome, and I'm going to put in instruction as my factor list, and I'm going to put my participant number as my label for these. Okay, and so what I want to do, if I hadn't unsplit that file by sorting it, what I would get, it would give me weird stuff, because I would have sort of been trying to run this on a sort thing. It would have been sort of stupid. So I'm going to go to my plots, request a histogram, turn off my stem and leaf. Okay, and then go through and paste that into my syntax file. So here, let's say so I'm evaluating my graphs for each cell. I'm going to go through and I'm going to run this. You get a whole bunch of stuff. But what this is going to do is it's going to go through and give me my histograms and box plots for each one of my cells. Okay. So Ari, how might I how might I describe this first plot here, this first histogram?
Positively skewed.
Yep, I've got some positive skew. But always when we're looking at this, always sort of think back to say, like, what are we actually measuring, right? It's fine to just say it's positively skewed, but what we want to do is think about, like, so what is this that I'm actually doing? Remember here, we have people who are, who we've shown a very sad film to and just allow them to just express their emotion, okay? So Ari, what are most people doing in terms of expressive behavior?
Sorry, I'm a little confused.
Yeah. So just sort of knowing that sort of what we've got is our expression rating, right? Where 1 is nothing at all, 5 is just like hugely emoting. Like, what's going on with these data?
Most people aren't really expressing.
Okay, right. And so this starts to give flavor to your interpretation, not just saying, oh, it's skewed. Like thinking about what does this actually mean? If I'm looking at this and this is my study, right? I'm saying, well, for this sadness film, it looks like there's not a whole lot of expression going on to that sadness film. Looks like people are kind of keeping it, even if we're just saying sort of express your emotions naturally. Most people aren't expressing a whole lot, but there are some sort of, as we get down, sort of people sort of getting more. And this is a tearjerker. This is a cry. Like some people will always cry and emote in sort of watching this film, right? And so we're getting some of that, but for the most part, people are sort of not exhibiting a whole big amount of expression. Okay, so Ari, for the purposes of our screening, are we too concerned about this distribution?
No.
No. Not really, right? But it's always nice to know, like, with these and thinking about, like, is my study doing what I think it should be doing, right? Is there stuff going on, right? And so here I would say that we got a skewed distribution with most people reporting low levels of expression, with people sort of, as we trail off, people being more emotive, okay? Down here we looking at my sadness inhibit, okay? So these are the folks who are watching the same film as the last group, but they just told to inhibit all emotion, right? Rachel, you had said we're seeing some restricted range going on here. What are we seeing in this graph?
Just that score is only ranged from like 1 to 3.
Mm-hmm. And really only 1, 2. We've got like one person. Looks like they sort of hit that 3 level, maybe 2. I don't know. We'd have to go through and take a look, right? And so just what am I phenomenologically with my data? Like, what am I sort of seeing happening here?
That most people are not expressing.
Yeah. So these are people who I'm told to inhibit, and so it's at least sort of visually, right? It's looking like that was effective. It's shutting things down, really restricted the range here. Okay. We should look down through looking at Natalie. How might you describe this histogram here?
Well, it's like unimodal, but it's not quite like normal, but kind of falls along that pattern range.
Mm-hmm. Wonderful. I would say that you didn't describe it as unremarkable. That's good. I might call this one kind of symmetrical, right? It looks like we've got kind of most people kind of hanging out there, sort of in the middle. Some people with low levels, some people with high levels. So these are people who watched a funny film and were allowed to express. Are we seeing differences here relative to here? Yeah. We're seeing for this funny film, we're just seeing a higher level of just baseline emotion here, right? For the sadness film, it was very skewed here, kind of symmetrical. Some people high, some people not so much, but sort of definitely seeing more emotion type behavior going on. And then here we've got our last condition. We've got our humor inhibit. Allie, what are we seeing here?
So for people who watch the funny film and are told to inhibit emotion, we're seeing that there's more inhibition of emotion, but it's a little bit, I don't know. I mean, there are some people who still kind of were a little bit expressive, or kind of, it's not as skewed as the sad film.
Yeah, right. So sometimes it looks like, if I'm just looking at that, it looks like really sort of my ability to inhibit emotion is maybe dependent on what type of thing I'm trying to do, right? If I'm sad and trying to inhibit emotion, maybe that's a little bit easier than if I think something's funny and trying to shut that down, right? Generally, are people doing a good job, an okay job with this? Yeah, but some stuff's leaking through, right? Maybe more so than we would see with the other stuff. So talking about this as a skewed distribution, describing it as such, but just the other thing too, this data screening is kind of tedious, and you kind of feel kind of formulaic and stuff like that. If you start thinking about, like, what does this actually tell me about my data? Now, for problem sets, you might not care what it tells you about your data, and that's understandable. But for your own stuff, this is where you're going to start sort of understanding, sort of, did my stuff work? Are there things that I need to go through and check? Sort of, are these data doing what I think they were supposed to be doing? Starts to give you a much better understanding of what's happening in your study than just sort of running numbers and reporting skew kurtosis and things like that. Okay. If we go down through and take a look at our box plots, right? What are we seeing here? Eric, can you kind of walk me through what's happening with this with this box plot, and again using kind of box plot terms in terms of what's happening with this?
So there's a difference clearly with the rumor expression. The expressive emotion, like the mean is higher.
Okay, are these means? In our box plot, what's this? What does this midline represent in our box plot?
The median.
Median, right? Exactly. So, and this is what's nice about box plot is box plots are constructed the same way. I can fool around with my histograms, get all sorts of weird stuff depending on sort of how I bin my stuff. Box plots are the same. Midline's always the median. The bounds of the box are always first and third quartiles. Whiskers, sort of farthest within 1.5 times the inner quartile mean. So there's just sort of a little bit more comparability we can go through. So yeah, median expressiveness is higher for my humor express, right? What else is going on here?
For both of the inhibit conditions, the median seems to be at 1. I can't really tell on this humor inhibit.
Yeah, actually here, median is 0. So we've got a floored out thing going for sadness inhibit. Median value is 1 for humor inhibit. So we've got some differences there. Yeah. What else are we seeing here?
There's a wider range for both of the express conditions.
Okay. Getting the full range with my express conditions, but again, seeing that skew, right? My first quartile and my lowest level here is 1. But we've got some people with sort of lots of expression here. We've got sort of perfectly symmetrical. That's part of our scaling thing, right? And then sort of maybe what's the last thing, Erica, we might sort of notice about this?
There are some not extraneous or extraneous values?
Extreme values.
Extreme values for humor inhibit.
Okay. And this starts to become important for you SPSS users, making sure that you indicate that you want it to label these marks by your participant number and not just case number so that you don't get confused on sort of who's who. But it looks like I've got case number 242, 294, 85, 102 are for my humor inhibit. We're having scores of 4 and 5, but these are falling sort of beyond 1.5 times the inner quartile. So these are folks who tried but failed to, or maybe they didn't try, maybe they just ignored and left themselves in the seat there. But we've got some people who sort of weren't able to keep things shut down here. Okay. So, any questions about the types of things that we're picking up in our plots and our descriptive statistics here? Okay. So, Robert, what's the last thing I might want to do here?
Look at e-scores?
Yeah. And look at my standardized scores, right? So what I'm going to do is I'm going to just take a shortcut, and I'm going to take my syntax for my descriptives, and I'm just going to get rid of that because I don't need z-scores on my z-scores. I also don't need skew and kurtosis levels. I'm going to get rid of that, and then I want it to give me z-scores for my expression condition there. So I just went through and sort of modified my syntax, go through, run this. Oh, whoops. What did I not do? Why is this not a useful descriptive, a useful set of descriptives for me to look at?
You didn't separate them into groups.
Yeah. So I need to go back through, go up here, re-split my file. And now my file's split. I'm going to rerun this. There we go. Okay. So with this first one, right, always a check, right? If I've done this correctly, mean and standard deviation for my z-score should be 0 and 1 all the time. Now, Ali and Robert stated it's like ultra precise, and we'll give you some decimal times 10 to the negative 50th or something like that. You're fine there. But for SPSS users, if you notice here, right, my mean is 0, but my standard deviation isn't 1. If I've done this correctly, sort of that will sort of add up. So just keep an eye on that. But Ali, as I'm going through and looking at this, do I see anything potentially problematic in terms of my z-scores for my individual conditions?
Not too much. I don't think so. I mean, for the Humor Express, the minimum is a little bit larger, or like, I don't know, but it doesn't seem like too much of an issue.
Did you say humor or did you say humor?
Oh, sorry, Humor Inhibit.
Yeah.
For maximum.
Yeah.
But range is wider.
Yep. My humor inhibit, so I've got a high-ish Z, and I would probably say that's worth noting, right? Allie, is it something that's going to, that I'm hugely worried is going to influence my data?
Probably not too much.
Probably not too much. I mean, this is what I'm looking at in my box plot. If I go through and I take a look at my histogram, they're all sort of part of the thing. And this starts to be, again, we always want to be cognizant of our of extreme values, but really, for the purposes of our work, particularly for things like this, I mean, like, even if I max out my value, there's only so high this rating can get. It caps at 5, and that's the end of the story, right? It's not like income or sort of some type of thing or landmass or in other areas where it could be exponentially larger than my sort of next adjoining thing. Here would want to take a look at this because this, again, remember the whole purpose of sort of this analysis is we've got a manipulation check. We're saying, was this thing effective, right? Well, it might be relevant to note that seems like, yeah, for my people I instructed to inhibit, it looked like people were pretty good at that. For people watching this funny film, looks like some stuff snuck through. We've got some higher z-scores here. And then if I go through and I flip back to my z-scores, right? I've got my person here. I've got my high value being someone in my humor inhibit condition who's scoring 3.1 standard deviations above the mean, right? And then I've got a couple other scores here that are sort of high-ish. But again, probably not anything I'm worried about, and certainly nothing that is going to keep me from moving forward and running the analyses that I want to, but something that I should probably take into account and sort of say, hey, sort of these are the things that kind of went on. Okay. All right. So if you go through and take a look at your output, here is just kind of a sample write-up of what we've got, right? We've got missing data, 3 cases with our missing express scores. We've got participant number and what condition they were in, right? Just so we know if there's not anything systematic. No problem of problematic values. We're going to go through, got rid of those 3 folks, and going to proceed with sort of our remaining people here, right? Here we're looking at our distributions. We're giving numbers for our skew and our kurtosis, kind of just describing what's going on with our histograms and our box plots, making sure that we're including our sample sizes. Again, the idea that this is just kind of a report that I could run down through and sort of get a good sense for what's going on with the data. My extreme outliers, extreme values, nothing much going on here, nothing much going on here, nothing much going on here. Here, minimal evidence of extreme values. You might want to sort of, you could make a report and say, hey, sort of there's some stuff kind of going on here if you want to. But again, for screening purposes, it's not going to be anything huge. But it might be worth saying, hey, there were a couple people who kind of snuck out. We're going to ask for a Levine's test when we actually run our ANOVA model, but that's where that's going to come from. Looks like we may have a potential for violation of homogeneity of variance, so wanted to keep that in mind. But in terms of recommendations, got 3 cases with missing values, possible violation of homogeneity of variance, and then kind of just writing this up. We're saying relatively balanced, minimal missingness, distribution of cells were generally not normal or symmetrical, but deviations unlikely to be problematic for underlying assumptions, particularly given the small or the large size. Screening not providing evidence, providing evidence for potential violations of homogeneity of variance. Recommend that we proceed with our ANOVA with adjustments in our omnibus and follow-up tests for non-constant variance across my different groups. So really the main thing here is wanting to note that it looks like when we run this Levine's test that the variability of expressive behavior may differ whether or not I'm talking about sadness express, sadness inhibit, humor express, and humor inhibit. And does this make sense, Natalie?
Sorry.
Yeah. Does it make sense that the variability or sort of person-to-person differences in expressive behavior might not be identical in people sort of watching different films and sort of under different instructions?
Yes.
Yeah, right? It kind of makes sense, right? In one condition, I'm telling people not to express anything. And if I'm telling people not to express anything, should I expect a whole lot of variability in my scores? Probably not, right? And if I've got people watching sad things versus funny things, I would maybe expect more variability in expressive behavior in response to sadness eliciting stimuli than amusement eliciting stimuli, right? And so, sort of the very nature of what I'm asking people to do, I shouldn't be super surprised that I might have a violation of that homogeneity of variance assumption. So this kind of makes sense, right? So again, what we're doing is we're just thinking about what did I do? What are my data telling me? And so then does this make sense? How do I sort of think about this? Okay. Questions on the screening with this? Okay, cool. So let's go through and I guess we can go through and do this. Pull up your handout. We're actually going to go through and we're going to run our analyses here. Okay. So if we go back to our data set, what I'm going to do, I'm going to sort this real quick to make sure that sorts off, because otherwise you'll try and run a 2x2 ANOVA model with sorted with split file data, and you're going to get sort of big errors and it'll be confused. So make sure to shut that off. I'm going to go to Analyze, and go to General Linear Model here, and I'm going to go to Univariate. Okay. What I'm going to say is I want expression rating to be my dependent variable. My fixed factors are going to be my film condition and my instruction condition. Okay, we put those there, right? I don't have any random factors, so I don't need to worry about that. I don't have any covariates. I don't have any weighting things. So we're all good there. Don't need to worry about anything. Okay. Go to my model. We're just going to leave this at full factorial. If you want to get fancy and crazy, you can go through and build custom terms, things that you're probably not going to worry about this. Generally, our models are going to be full factorial. Here's certain types of sum of squares. If you get into some crazy stuff, you can see that there are other types that you can go through and do. Don't get fancy unless you need to get fancy. Have a good reason for getting fancy if you're going to do so. So we're going to go through and leave that alone. So I can go through contrasts. We're not going to worry about this. Contrast stuff, we need to get in to do some other stuff because SPSS isn't going to do it right. Plots. What we can do is we can... SPSS plots are garbage. We're not going to worry about that. Post-hoc. This is a dangerous thing because what this is going to do is it's going to give you comparisons on a bunch of tests that don't make any goddamn sense to be looking at in the first place, but it's going to still control for them, so stay away from this. Here, what we can do is we can go through and take a look at our estimated means and our marginal means, so we can go down through and request those. There's other stuff you can do. We won't worry about it right now. But I hit continue. You can go to options. I'm going to ask for descriptive statistics, estimates of effect size, homogeneity of variance test, and then we'll leave that here alone. Okay. All right. I'm going to hit continue here. I'm going to paste that. All right. 2x2 ANOVA. Okay. So this is just going to go through, going to run this, and this is going to run my ANOVA model. Okay. Oops. All right. So here's my results for my ANOVAs. Okay, or for my ANOVA one singular ANOVA. I ran one ANOVA here. All right. So here's my between subjects factor. Again, always sort of look through this and make sure that you got a good handle on stuff to make sure that things are looking sort of the way we expect them to look. Here, looks like we have 91 people who were assigned to the sadness film, 98 to the amusement film, 94 were instructed to express, and 95 were instructed to withhold. That all makes sense. That's looking pretty good, right? Here, we've got our descriptive statistics, okay? And so what we've got is we have people who watched the sadness film, number of people who were told to express, number of people who were told, or people, the mean and standard deviation people who were instructed to inhibit, and then Robert, what's this total column correspond to?
The total variability?
Well, yeah, if we took a look at that, but this is going to be my marginal mean, right? This is the mean score for everybody who was watched this. This is the mean expression score and the standard deviation of everybody who watched the sadness film. Okay, so again, what does Robert? What does this total column correspond to? Is that a main effect or an interaction mean?
That would be a mean.
Yeah. Right. So here's my main effect of if I'm looking at my total, and then if I go down through and I take a look at amusement, from people who watch the amusement film, here's the express, here's withhold, and here's the total. Total is my main effective film. Average expression rating for sad film, average rating for amusement film, ignoring a cross condition. So I've got my main effect here, right? And then down, if I go through and look at my total, here's everybody who was mean of everybody who was told to express, everybody who was told to inhibit, right? Another main effect, right? Collapsing across film, here's the mean expression for everybody who was told to express, everybody who was told to inhibit. And then Rachel, what's the total of the total down here?
Everybody?
Yeah, that's my grand mean, right? So remember when we went back through and we were calculating these components, this is the grand mean for everybody, all 189 people in the thing. Okay, so be careful to go through. You want to be able to sort of make sure that you're mapping on sort of where these means are coming from, because if we start to get interaction terms and effects like that, this is where we want to go back through and take a look. All right, going down through, and we've got our Levine test. Okay, now our Levine test is telling us whether or not we've got violations of homogeneity of variance. Basically, what this is doing, Robert and Allie, you have to do a little bit of finagling to tease this out in Stata. But what this is telling us is whether or not we have evidence for evidence of difference population variances across each one of my individual cells. Okay, and Erica, what are we seeing here in this table?
I don't know. I'm sorry.
Okay, so remember that there's a bunch of things that we've got here. We don't have to worry about that. So we're just looking at based on the mean, right? So just based on this first line here, you can ignore everything out. That's just different variations. Does it look like we have violation of homogeneity of variance here? Or evidence for a potential violation of homogeneity of variance?
Maybe because it's significant, right?
Yeah, right? So, and again, we've got a low p-value, right? Which is saying that based on the data we have available, it looks like it's possible that the variance in global expression ratings maybe isn't exactly the same across people. The hypothetical populations of individuals watching sad films allowed to express, sad allowed to instruct to inhibit, amusing allowed to express, amusing instruct to inhibit. Again, this isn't a shock, right? We kind of saw that, right? Remember when we looked at those box plots, they were kind of all over. Looks like there's differences. Just based on what we asked people to do, kind of makes sense that there would be differences, right? And so between this and just reasonably thinking like, yeah, it kind of makes sense that we would see differences in the variability of expressive behavior across people in these different conditions, I'm pretty comfortable saying, okay, what I want to do is I go through and proceed, assuming that probably I have some violation that I'll need to be thinking about, okay? So if I'm thinking about down the road, sort of spoiler for when we start to get into follow-up tests, I need to be considering the possibility that, okay, I've got a relatively balanced design. So that's pretty good. I don't know that that I have wide differences in sort of the overall precision of my estimates, given my cell sizes are pretty similar and pretty large. But what I do have is probably need to consider the fact that sort of I've violated homogeneity of variance, that the variability isn't the same across these. And so thinking about that and sort of thinking about my game plan for follow-up tests, effect sizes, and things. Okay. And we had noted that in our screening, and so, but just want to keep that in our minds. Okay. So now we go down through and take a look at our ANOVA table. Okay. So here, there's some things that you can ignore in SPSS. Here's your corrected model. This is just your sum of squares cells that we had talked about. SPSS provides it. You don't need to worry about it. You can ignore that. Just know what it is, but sort of you can ignore it for right now. Here's your intercept. Ignore that. That's just a test of whether or not mean values for everybody is 0. It's not. That doesn't have anything to do with anything, so you don't have to worry about that. But down here you see effective film, effective struction, film by extraction, error, and then we have your corrected total down here. Ignore total. Total doesn't. This total includes your corrected model and maybe your intercept. I can't remember. Yeah, it does include your intercept as well. Ignore that, looking at your corrected total. Okay, so relative to what we went through in terms of the hand calculations, so we went through and we found our effective film, effective instruction, film by instruction, our error, which is our within, and then our corrected total, that's going to be our total. Okay, so looking at the output from our table, Robert, what are we seeing in terms of our hypothesis tests within this table?
Seeing a very high F statistic.
Yeah.
Very high.
Right. Yeah. And so very high F statistic for what?
The intercept.
Okay. Ignore the intercept. Intercept, we don't need to worry about intercept. Intercept is not anything that's useful for our purposes, right? What about this effective film?
Also seeing a high F statistic, but I guess I'm getting thrown off because I'm looking at the film and the.
Okay, so let's just focus on the film. So have a high F statistic for film and a very low p-value, p less than 0.001. What is this? Yeah, 1.03 times 10 to the negative 7th, right? So that's super small. So ton of evidence for a main effective film. And so what does that main effective film mean?
So we have sufficient evidence to reject the null.
Yep, sure. But what does practically, what does that main effective film mean for expressive behavior?
That the film does display an effect that we would expect to persist across conditions.
Yeah. So collapsing across instruction condition, we're seeing that based on this film, and I don't know, I'm saying this is saying that we have strong evidence of differences in expressive behavior across the sadness and the amusement films. Okay, So ignoring condition, there are differences in expressive ratings for people who are watching the film condition or watching the sadness film versus the amusement film. Okay. And so, Robert, what else are we seeing? So tell me about this effect for instruction. What are we seeing here?
So we're also seeing a high statistic with a low p-value, so enough to reject the null in terms of like conceptually, we're looking at like collapsing conditions that affect that we'd expect a condition from the instruction condition.
Mm-hmm. So basically what I'm seeing here, without even sort of going through and looking at things, looks like we have an effective instruction, right? Looks like that people told to inhibit their expression are showing different levels of expressive behavior than those allowed to express freely. Okay. And then, Allie, what about that interaction? What are we seeing there?
It doesn't look like it's significant based on the p-value. I mean, or significant, meaningful. I don't know. Basically, there are two main effects, but it doesn't matter. Like based on, like they're not dependent on each other.
Yeah. So if we're taking a look at this, right, we're saying here probably we don't have strong evidence for a dependency for the effective film and instruction, right? That p-value is going to be associated with pretty weak evidence of much of anything. We're not going to say no evidence. It's, someone could say, oh, we have a trend for this. Now that's problematic. Are we trending towards it or away from it? So we don't know, right? It's not hitting that 0.05, but is that sort of categorically different than a 0.05? Probably not, because 0.05 isn't real strong evidence of much of anything anyway. So, whether or not we wanted to move forward with an interpretation. Objectively, we're saying that these data don't provide strong support for an interactive effect of film and instruction on expressive behavior. Okay. But we're going to go through on Wednesday. We'll pick it up just for didactic purposes to go through and sort of follow this up anyway. It looks like there might not be nothing there. It's just we don't have real strong evidence sort of based on some of this stuff. Okay. But so these are our omnibus effects, Rachel. But we've got, it looks like what we have is maybe a main effect of film, maybe an effect of instruction. Do we need to run follow-up tests to interpret what's going on with that film and instruction main effect?
You'd probably want to see what direction the effect is in, so you'd probably want to do a t-test or something.
Okay. How many levels do I have to my film condition?
2.
And if I have effective film, do I need to run a t-test?
I guess probably not.
Yeah. I mean, what I can do is I can just look at my mean values, right? So I've got a main effective film. So if I go up to my means and I say, well, people in the sadness film had a mean of 1.71. People in the amusement film had a film of 2.45. There's only two. If there's only 2 levels to my condition, my F-test already tells me that it's. I mean, I have everything that I need to know. When I only have 2 levels of my factor, if I see that I have evidence for an effect, I just look at the means and say that's my effect, right? Here, it's nice because for our main effects, there's no need to do any follow-up tests because this F is everything that I need to know. Anybody remember the relationship between F and T? Remember that an F-test with 1 degree of freedom in the numerator is just, it collapses into a t-test. If I take the square root, someone have a calculator. Someone take a square root of 30.684. What do you got, Robert?
5.539.
Yeah, that's going to be my T statistic, right? Well, it might not be because factoring variances out a little bit different. But sort of basically what I've got is I don't need to do a follow-up test with my main effect. Same thing with instruction. My table, my effect is saying so that controlling for effective film, I have an impact of instruction. If I go up and I say, well, my express had a mean of 2.47, my withhold at 1.73, that's all I need to know. I don't need to run any more statistical tests here because I've only got 2 levels of my factor. And so now, Rachel, what if I had in for my instruction condition, I had express, withhold, and exaggerate, right? And I would have found a main effective condition. Then do I have to run follow-ups?
Yes, because then you can't really tell the direction.
Yep. In that case, then I would have to run a follow-up because I don't know. My omnibus test is just saying that across those 3 levels, I have differences somewhere, but the omnibus test doesn't tell me. But this is nice and something to think about as we're going through and running our ANOVA designs and creating these. If I've only got 2 levels of my factor, makes it a little bit easier to start to go through and do things because I don't have to necessarily check this out because I already know. Here I have very strong evidence for a main effective film where I'm seeing more expressive behavior in response to my amusement film than my sadness film. I've also got a large effect for instruction where I'm seeing more expressive behavior in the people who are allowed to naturally express relative to those who are told to inhibit. And then some questions about whether or not those 2 are dependent. Not strong evidence of it, but something we'll kind of follow up just to talk about how we would probe an interaction next time. Okay, but what are we going through? Does all this stuff make sense given what I've asked people to do? Yeah. And Erica, based on these data, is it reasonable to claim evidence in support for my manipulation? Because that's the whole thing we're doing. This is a manipulation check. Yeah, right. My my inhibit manipulation isn't perfect. Not everybody were perfectly successful or perfectly adhered, but on average, it looks like it's doing what it's supposed to do. All right. Questions on any of this? Awesome. Okay. We're in a good spot. We can spend our last class on Wednesday just working through follow-up tests and sort of considerations and contrasts and how we go through and do these and how we integrate post hoc tests and contrasts and make sense of interactions and things like that, which is a good place to be. Go through, keep working on your problem set 6. Sounds like you're in a good place. People are moving forward with stuff. Let me know if you have problems with things. Don't worry. I'm happy to reply to emails sort of at any point in time. Don't worry about I don't want to bother Josh because of things. I'll get back to you as soon as I can. I know that things get crazy towards the end of the semester, and so don't want you, if you guys have set aside time to work on stuff, I don't want you to be hanging out and sort of waiting for me to respond. So I'll get back to you as quickly as you can, but let CJ or I know if you have questions. Otherwise, have a good holiday. We'll catch you next Wednesday. All right. See ya.